For it.
Here we will present our force-controlled approach to bipedal balancing on dynamic terrain with Tallahassee Cassie. Joint positioning control techniques are very common in the field of bipedal balance for robots. They work especially well when the ground is rigid and non-moving. However, once the ground starts to move beneath the robot's feet, such as soft ground or a sudden drop, or what we call dynamic terrain, then the algorithms tend to work less well. So we adopt a simple force-controlled technique for balance of bipedal robots, which theoretically should balance equally well on dynamic terrain. And here is our control architecture. It uses very simple PD-based force control to regulate the pelvis position of the robot, while rendering those forces into joint torques, not joint positions. For our experimental platform, we will use a Cassie series robot from Agility Robotics called Tallahassee Cassie. And we will make some major simplifying assumptions about this robot, only pretending to know the weight of the robot and its kinematics. So let's look at an example. Here we have Tallahassee Cassie's legs being spread apart by our researcher, where the pelvis is being commanded to split the difference between its two legs. The blue circle in the middle is the actual measured pelvis position. As a demonstration of soft terrain, we put one of the robot's legs on soft packing foam while subjecting it to small pushes. We further lifted one of the robot's legs to show that the robot maintains balance in spite of the entire base of the robot being shifted. A nice feature of force control is that even when we lift this robot higher, when the leg slides like that, it still can maintain balance. Now let's finish with a box drop sequence one more time. This time you'll notice there's no safety tether.
Alright, 3, 2, 1.
Now let's watch that from a different angle. Now we'll rewind the footage and show it at 1/8 speed. Note how the foot falls on its toe while it maintains balance and eventually regains its footing. All is an emergent property of force control.